So this is going to be welcome. This is going to be the sources of magnetic field. And so we're trying to figure out about coils and the like. And we're going to introduce, we're not going to justify, we're going to introduce a thing called Boyer-Savart law. And it looks a bit complicated, but it's just an equation. And then we're going to use Boyer-Savart law for various very stylized configurations. And then we're going to turn around and we're going to do force in a parallel current wire carrying wires. And we're going to talk about Ampere's law, which is another way of sorting stuff out. We'll introduce magnetic flux. We'll introduce Gauss's law for magnetism. And we'll introduce the displacement current. Now, in truth, I tend to emphasize the beginning of this chapter more than the end. It doesn't mean to say that the end will not be included, but the end is, I think, the harder analytical stuff, which basically takes us on to Maxwell's 4 equations, which we touch on. So I tend to focus more on the beginning than the end. So don't know it all, but make sure you can answer the questions. If you've got to make some hard choices here, make sure you can answer the beginning questions as opposed to the end questions. Okay. Boyer-Savart. So, okay, we know that when a current flows through a wire, it creates a magnetic field. That's how electromagnets work. Okay. So we'd like to know what the relationship between is the current flowing through the wire and the geometry of the wire's shape and a point in space. Because we'd like to know, just like we'd like to know what's the gravitational field caused by these 4 planets, what's the electrostatic field caused by these 4 charges. I want to find out what's the magnetic field at that point caused by these 4 bits of current carrying wire, these 4 lengths end to end. So we take a general case and we look at this and we say, well, let's not imagine the whole wire. Let's just take a little bit of our wire. So let's take a little bit like that. Let's do it in red. So here's my little bit of wire, that little bit. And it's got a certain length, ds. And then I'm going to take a point somewhere over to the edge of the wire. And I'm going to say there's a little bit of magnetic field called dB at point P. I suspect I need to know the distance from my little bit of wire to that point, so that's r. So r is a scalar number. And I expect I need to know the direction. So r hat is a unit vector. So rule number 1, don't get confused between your r, which is a scalar length, and r hat, which is a unit vector. The different animals doing completely different jobs. So current flows in the direction of ds. That's fair enough. If I think about this, what I would see is as the current flows like that, I have a right-hand corkscrew rule, so the magnetic field, put my thumb in the direction of the current, and my fingers curl around in the direction of the magnetic field. So these are all my B lines, B. So basically, if I have my thumb pointing from left to right on this piece of wire, I would expect this to be coming up and out of the page on this side, and down and into the page on that side. So there's my B direction. So it goes up and out on one side and down and in on the other side. And, okay. So we say, consider a magnetic field, little bit of magnetic field, dB at point P caused by a current flowing through a length of wire ds. The position vector relating the length element ds to the point P is r. So that should be position vector. Oh, so that should be r hat. And can you correct this, please? That's a mistake. That should be r hat. Okay. And down here again, that should be r hat. Man, I need to work on this. This section needs some work. So we say, okay, and along came Boyar-Savat. And it's kind of like it's not justified. A hand-waving justification is my little bit of electric field goes as 1 over r squared compared with a charge. So my little bit of magnetic field should go as 1 over r squared compared with a monopole. I don't know what a monopole is. I don't think I've ever seen one. There's a constant. There's always a constant. If I have more current, I expect more magnetic field. That just makes sense. If I have a little piece longer wire, then I expect more magnetic field caused by that little piece. And if the direction changes, I expect the value to change. You know, if I have a piece of wire like that, and so there's my ds, and my point is here, then my r hat would be in that direction. And if my point is there, my r hat is in that direction. They're the same distance from my little point. So I expect there to be an angular effect, because as you go further, as you go more 90 degrees, you're going to be further away. Yeah. That all kind of makes sense, but I don't justify it. I don't know, the book doesn't justify it, just says here's Boyar-Savat. Well, here's the elements of Boyar-Savat. Mu naught is like epsilon naught, but it's for magnetism, so it's called the permeability of free space, not the permittivity of free space. And it's got these weird numbers. It's 4 pi times 10 to the minus 7. 4 pi is about 4 3s are 12. It's about 14 times 10 to the minus 7, but we tend to put down 4 pi. So if I do the integral, if I sum all these little bits up, it's just an integral, isn't it? I've got to integrate all these little bits. So the total magnetism is equal to, well, mu naught's a constant, and I is a constant, and 4 pi is a constant. So it's just the integral of ds crossed with r hat over r squared.
Is that integral in respect to r?
Yes. Actually, well, ds. Okay, yep. So, okay. So if I have a length of wire and I have a point there, then for each, let's draw a different diagram. If I have a length of wire and I have a point here, then that little bit's got a certain r and a certain r hat, and that bit's got a different r and a different r hat, and that bit's got a different r and a different r hat, and that bit's got a different r and a different r hat. It's a pain. It's not impossible, it's just a longer integration. So we tend to, I'm going to skip this slide, we tend to cheat. And we tend to cheat by taking the simple case, which is we're going to look at a lot of symmetry. And the thing with a classic symmetry is a circle. So what we're going to say is we have a circle of wire. Currents go in loops, so this is not so unreasonable. Let's make it a nice pure circle. And let's say I'm interested in the point in the middle. A couple of advantages. First of all the r's are the same. That's kind of nice. And in each case, my dr is at 90 degrees to my r hat in every case. So there's some symmetries that make my integration much easier. So we say a current carrying wire is bent into a complete circle. Use Boyar-Savat method as taught in class. So I want to see this derivation. To show B at the center of the wire is B equals mu naught I over 2R. And please, if you don't know, don't work back, because I can find it. It just takes me 20 minutes to find it, because things just don't add up. All the steps are not there, so I get suspicious. And I start looking at these logical steps that are just missing, and it ticks me off. So if I could take points away from you, I would take points away from you, but I can't. And it might not be that you get caught because I don't look at the name. So I don't say, oh man, I'm going to get him or her next time. It's that it gets me a bit more frosty for everybody in the class. So just if you don't know it, it's not going to be worth 9 points. You know,
1 point is 10%.
1 or 2. So maybe 10 or 20%, but that's the way it goes. That's life. But it's not going to be like your whole grade depends upon this. So just learn it. It's going to be on the test. It's going to be on the test. So learn this skill. It's money in the bank. And if you don't learn it, then, mea culpa. I didn't learn it. Okay, but man, you try and trick me on this. And I cry. I go home and I just sob. So current carrying wire bent in a complete circle. Use Boyer-Servat method taught in class to prove this. I wouldn't ask you to prove it. I'd ask you for a value of it. I is the current flowing through the wire and R is the radius. So let's visualize it. So we visualized it. There's my R. There's my R hat for this little ds. They're at 90 degrees to each other. Oh, I'm sorry. I've been drawing. In fact, yeah, that should be. So where's my pen? The R hat is there. That's bad, Bonnequist. The R hat is actually on the wire, pointing towards the point of interest. So what do I recognize about this? I recognize, well, first of all, I write down Boyer-Servat. You see, we've got some points just for writing down Boyer-Servat. So write that down with a unit vector there. R is constant. So let's take it outside. So it's mu naught I over 4 pi r squared integral of ds crossed with r at r hat. If you look at our diagram, r hat is perpendicular to ds and r hat is equal to 1. If it's perpendicular to ds, then ds r hat times the sine of 90. What's the sine of 90 equals 1?
We have to say that r hat is equal to 1.
I know that r hat is equal to 1, so you don't know. But I would like you to have down that line there and that line there. Then I know you know what you're doing. But I'm doing explanation on the side here. So that goes to 90, and this is equal to 1. So ds times r hat just gives me ds. Yeah. Integral of ds. What's the integral of ds? It's your circumference, isn't it? It's the length of your wire. L, if you like. But that's going to equal L, which equals 2 pi r in this case. So we have mu naught I over 4 pi r squared times 2 pi r is equal to mu naught I over 2r. Little r, of course, is equal to big R by definition, because I just said that up there, said that there. So B is equal to mu naught I over 2 pi r. There it is. Substitute in your I, substitute in your... In a test, you could leave mu naught by itself, because we've got other questions to answer. I don't know about the homework. I don't know if I ask you to do it in the homework. And then 2 times R. Got to be in meters, got to be in amps, but it works out nice. Gets you answer in Tesla. Yes?
In the very first equation for the law, where does that 4 pi come from?
Oh, I have no idea.
It's just one of those transcendental.
Yeah, I have no idea. It's like, I never, and the sad thing is it never even occurred to me, It's like,
4 pi is weird.
it is, and it's also in your mu naught, and it's in the equation. So it's like, okay. So, what would you get? You're going to get something more like this. A current carrying wire is bent into a semicircle. Yeah, half a circle. Okay. And it says, using the method of Boyer-Servat taught in class, determine the value of B at the center. So here's my B at the center. Current going through the wire, so I is equal to 5 amps. And the radius R, I'll show it there, but it's for this, R is equal to 2 meters. So, let's, from the beginning, let's recognize there's 2 classes. So what can I do as a teacher? I can give you sections of a circle. Semicircle, third of a circle, quarter circle, 7/16 of a circle. I suppose I could give you 3.5 circles. But it's got to be based on a circle, because that's what we've learned to use. Not going to go with a rectangle, not going to go with an ellipse, going to go with a circle, but a fraction of a circle, something like that. That's one thing I can play with. And then the other thing I can play with is I could give you the radius, and that will define the circle, or I could give you the length of wire. It's like I can define a circle by telling you its radius, or I can define the same circle by telling you its circumference. So they're my two choices. I can tell you the length of the wire and tell you it's a third of a circle, in which case I gave you the information you need to calculate the radius, or I can tell you the radius of the circle and tell you it's a third of a circle, in which case I gave you the information you needed to calculate length. So those are the two ways in. So fraction of a circle will change, and the way I come in will change. Here I've given you the circle. I've given you the radius again, so we'll just go through that. So the first thing I'm going to do is I've visualized. There's my B. Here's my delta S, and here's my R hat. And I say, let's have a look. What was that? B is equal to, what was it? Mu naught I over 4 pi. It rhymes, doesn't it? Mu naught I over 4 pi times integral of ds cross r hat, not r arrow r hat,
Divided by 2, right?
divided by r squared. Okay?
If it's half a circle, it's in a half hour.
No, half a circle is just half the length of wire. It's still the same. The radius is how far from the middle of the circle. A semicircle is what I've drawn. It's half the circumference of a circle.
But the ds is not going to be half of.
I will integrate over half the length, but not over half the r. Half the r is there. That's not the same thing. I'll integrate over half the length, but I'm not going to change my r, because my r is the size of my circle.
But what I mean, should it be ds over 2r squared?
I'm going to get to that later, but r does not change.
No.
So it's not 2r squared. You'll see what it comes out of. But if I mess with that r squared, it's going to mess with the size of the circle. So just leave it as it is. What's going to change is your integral of ds, which we'll get to. Okay? You'll see it. So then what's the first thing I say is? First thing I say is r is constant. Let's not, please. Let's not. So that means that b is equal to mu naught I over 4 pi r squared times the integral of ds cross with r hat. And then the next thing I say is ds is perpendicular to r hat, and r hat equals 1. And that enables me to say, oh, well, b is equal to mu naught I over 4 pi r squared. So if r hat is 1 and they're at 90 degrees to each other, then the sine of 90 equals 1. So this just comes down to the integral of ds. So I'm compounding a couple of steps there, but I don't mind that. You know, you just told me that ds is perpendicular to r hat, and r hat is equal to 1, so I'm comfortable with that. So now we say, well, let's have a look. This is mu naught I over 4 pi r squared. And that integral of ds, what will the integral of ds be? 2 pi r over 2, because it's a semicircle. If it was 16/17 of a circle, it would be 2 pi r times 16 over 17. If it was a third of a circle, it would be 2 pi r times a third. In this case, it's 2 pi r times a half, because it's half a circle. So this equals mu naught I pi over 4 r. That pi goes away. Pi goes away, pi goes away, 4r, yeah, okay. So in this case, it's going to be mu naught I, what was I? 5 over 4 times r. R was 2. So in a test, I would write this down as 5 over 8 mu naught, which equals, and I go 5 divided by 8, 0.625. You know. And the reason why I'm kind of getting keen on this is because I got people leaving this as the answer, putting brackets around it and calling it T. And other people are working out and making a mistake on doing these last bits. And although it's math is part of the test. So I got people with square roots in the answer, leaving square roots in the answer. And it's like, no, you've got to work stuff like that out. So I'm really trying to get you to work things through to a decimal.
Is 5A okay?
Oh, she got a hand up. What?
So is DS always perpendicular to R?
For this geometry, because it's a circle and the tangent is always perpendicular to the radius, yes.
Okay.
And that's why I'm not going to do a straight line, because that's not always the case.
Okay.
And I'm not going to do an ellipse, because that's not always the case. So that's why we're deliberately picking the circle, because it makes that, we can do that simplification. You should.
Oh, for the test, can we leave it just at 5A? You know?
I'd prefer you to do 0.625, but, you know. But I certainly don't want to be left out here with mu naught 5 over some scribbly bits, you know. So work it out to this decimal, then I'm happy, okay? But don't worry about your mu naught. It's fine. You can leave it. In the homework, I might ask you to work out the mu naught, because I think sometimes getting the size, idea for the size of things is beneficial. You put it in a box so I can find it, and it's great.
What was the value for you now?
I can't, are we saying?
What was the value for you now?
It's, what is it? 4 pi times 10 to the minus 7. It's in your notes earlier on. Okay. I want to do another one. Sorry, this was physics 1, people. Remember this?
No.
Yeah, you should. So, quarter of a circle. Quarter of a circle. Wire bent into quarter circle. Oh, come on. Quarter circle. And it is made of a length of wire which is L wire equals 3 meters. I equals 2 amps. Want to know the magnetic field at the center? That's all I can ask you about, is the magnetic field at center. So, I know the L, but I don't know the R. But I have a little bit of DS, and I have a hat, and I say, want B there. So I say, let's look, B is equal to mu naught I over 4 pi times the integral of ds crossed with r hat over r squared. And so I say, oh, r is constant. So B is equal to mu naught I over 4 pi r squared. I should use little r just so that I'm not changing symbols halfway through. R squared times the integral of ds cross r hat. And I say, but you know, ds is perpendicular to r hat. And r hat has a magnitude equal to 1. So what that gives me is B is equal to mu naught I over 4 pi r squared. The 90 degrees means I don't have to worry about the angle, so I get ds times r hat, and r hat equals 1 gives me ds, so I get the integral of ds, which equals mu naught I over 4 pi r squared times 2 pi r over
4.
4. So this equals mu naught I, pi's go away, r. And let's look on top. I got 2, I got 16, 2 on top and 16 on the bottom. So that would be that, I think. Did I do that right?
Well, we need to find R out.
So the problem is I don't know r. So I would do this as a second bit, and I would say 2 pi r over 4 is equal to 3 meters. So r is equal to 12 over 2 pi meters, which equals 6 over pi. And then I would bring that back here and say, well, b is equal to mu naught I over 8 times 6 over pi, which equals mu naught I pi over 5 eighths of 40, 6 eighths of 48. And then I'm going to leave mu naught alone. I'm going to say I is 2. I'm going to say pi is pi. I'm going to work that out. And then I'm going to say over 48. I just get my calculator at this point. Don't worry about the mu naught. I'm going to say 2 times second, oh no, clear. 2 times pi is that, divided by 48 is that, and I get my 0.13 mu naught. That as well. And you know, sometimes what people do is they'll say, oh, this equals L. And it's true, it does. This integral ds equals the length of the wire, and you give them the length of the wire, but then you've got to figure out what r is, and I think you're doing it twice, and it's just... So my advice is you just recognize, oh, it's a quarter of a circle, so that's 2 pi r over 4. Get the thing as simple as possible, and then say, oh, I don't know what the r is. Let's work out what the r is. So rather than having L's and r's in your equation at once, just do it as one thing at the end. Yeah, something like that is going to be on the test. Want to see all those steps. Want to see that r equals constant. Wants to see ds is perpendicular to r hat, and r hat is equal to 1. You know, it's money in the bank. You know, if you're of a mind to, and you're how many people consider themselves good mathematicians? How many people kind of go, okay, so what you might want to do is try to do the one for a straight line.
I think that's on you.
Just decide it. I'd never ask you for it. I've not done it in years, but you know, it's that next level of calculus.
Straight line.
Yeah, doing a straight line. So you can try it. There's easier ways in physics of doing it, and we're going to get to those in a minute. But you know, if you're a good mathematician, you want to build up your skills, because the difference. So what's going to happen as you go through it? Certainly in physics is you're not going to get new stuff particularly. You'll get modern physics, which we've not touched on, which is a shame. But in terms of the 5 bits or 6 bits of physics that we do, it's not that you do new stuff. It's that you do more complicated stuff. And the way you deal with it is better mathematics. That's a fair bit of what happens. You touch on all the principles here, but you don't do the better mathematics. And I wasn't aware of that. I thought we'd do new stuff in my junior and senior year. And in fact, we went back and did an awful lot of the same old stuff, but more rigorously. And so I was completely unprepared for that. And they used math formulism to get rid of visualization. I wasn't at all prepared for that. And in engineering, I think, you know, you talk to people doing statics, and it's the same principles. It's just much more complicated. And you use matrices in order to be able to deal with that and the like. So my advice, whether you're engineering or physics, is don't be like me and try and get round the math. Embrace the math and practice. And even if you're not so successful that you become a mathematician, if you're better in a month's time than you were today, that's better. You know, so however good you're going to be, you'll be better if you're better at math. So just practice, and just none of it's wasted. You know, try and get out of what I had, which is that survival mode attitude of this might not be important because I might not be asked about it on some test. Try and get away from that and say, hey, I want to be a physicist, or I want to be an engineer, or I want to be an architect. This is going to be involved somewhere. I'm going to master it. I'm not going to let the course master me. I'm going to master the course. And you might not be perfect. None of us are. But you'll get much closer. So this seems like it's a harder question. And it is, but it's only harder in a little bit of a way. So let's work through this. So a current carrying wire is bent into a complete circle. Use Boyer-Savat law method as taught in class to show that the magnitude of the x component at B of B at A is given by this. Oh man, this is horrible. Look how complicated it is. And you know what I've learned the hard way is whenever I see stuff with like 3/2s in it, I look and say, hold on. Something squared plus something squared. And there's a 1/2 or a 3/2 power. That's something to do with Pythagoras. And I look at my diagram and go, oh yeah, look, there's my r, and here's my x, and here's my hypotenuse. Ooh, I think that's the square on the side. You know, c squared equals a squared plus b squared. Playing around in there. And the other thing I've learned to do is just have faith in my math. Just have faith that you can just follow your physics, do the right math, and you get the right answer. So I say, oh, so Boyer-Savat law says that B is equal to mu naught I over 4 pi times the integral of ds crossed with r hat over r squared. Okay. And you say, well, and even for this, if you think about it, if this is my r, this is the little r, isn't it? The little r is that r there, that r there, is not the same as big R. Big R is from my ds element to the axis. And little r is from my ds element to the point of interest. So they're not the same length, are they? So, but this distance from the ds element to the point of interest is still a constant. Because I'm on the axis. So it wouldn't work if it was up here or down there or over there, but it works on the axis. So I say r is constant. So B is equal to mu naught I over 4 pi r squared times the integral of ds crossed with r hat. And then I say, well, hold on, my ds is still at perpendicular to r hat, isn't it? And r hat is still equal to 1, isn't it? So I say, oh, ds is perpendicular to r hat, and r hat is equal to 1. So B is equal to mu naught I over 4 pi r squared times 2 pi big R, not little r. I've got to be careful about that. It's big R, isn't it? It's the circumference of the circle of the current carrying wire, and that is big R. Got it? Okay. I have a quick look at my answer, and I see there's no little r's in my answer and the like. Let's draw this guy from the side. So there's my wire, and there's my wire. And here's my axis. And here's my point of interest. And that there is my R. And that there is my R. And that there is my X. And I'm defining this angle here There's my angle. Okay. And when I had this thing in the plane of the wire, my magnetic field was like that, wasn't it? My magnetic field is at 90 degrees to the wire. So if I had a circle of wire and I was interested in the magnetic field there, that little bit caused a bit of magnetic field, and that 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 caused a big magnetic field. They all added up. That's what the integral was. And now I'm off axis, so here's my same piece of wire, but now I'm not there, I'm back here. So that one causes a bit of magnetic field, and that one causes a bit of magnetic field, and that one causes a bit of magnetic field, and that one causes a bit of magnetic field. And so what I'm forming is not a series of parallel arrows. I'm forming a cone of arrows. Because this thing is always at 90 degrees. The magnetic field is always at 90 degrees to the line from the element to the point of interest. Yeah? Yeah? There's my wire. Here's my wire. My magnetic field is always at 90 degrees. Wherever I draw it, my magnetic field is at 90 degrees. Yeah? So this is, I can't just add up all these values because of this. They're all pointing in slightly different directions. But here's the interesting thing. So first of all, is everybody kind of comfortable with the fact that this forms a cone of arrows? The one from that bit is there. Is everybody kind of comfortable with that? If I have, let me draw it on the board. Oh, let's try and draw it bigger on another sheet so you can see it on the video. Let's get another piece of paper. So the idea is, you know, that little element there causes a magnetic field like that. And the little element out here causes a magnetic field like that. So, and the magnetic field of the bit of wire caused by that causes a magnetic field like that, and then that guy causes a magnetic field caused like that. And so I'm not drawing this to this right sizes, but I get a cone of arrows as I go around there, I get arrow, 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 and then I go down that quarter, arrow, 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 and so I'm down to there, and then for that quarter, there, and then for that quarter, there. Yeah, so it's like a cone. Well, cones are interesting because that balances that, and the y components cancel out. Yeah. So opposites always cancel their non-axial component. This guy here, its non-axial component is cancelled out by that guy there's non-axial component. So these guys are always going to cancel. So all I'm left with is that guy and that guy, and they are in line with each other. So I only end up with an x component. There's no y component or z component. There's only an x component. Yeah? So with that said, I can come back here and I can say, okay, so that means that I want to take this value, and which is for one of them, and I want to multiply it by the cosine of my angle. If that's angle there, that's the angle there. Little angle, so big angle, little angle, big angle. So, agreed? Bit of geometry there?
No, why do we multiply for the other side?
Because I don't want that length, I want that length. I want the component of this answer on the x-axis. Let's go back to, why do I want the component on the x-axis? Because that's what I've worked out. That's what I've worked out. But it's y component of that one cancels with that one because it's a mirror of each other, and all I'm left with is the x. Okay? So I end up with that cosine theta. So, and then I just simply sit around and say, well, b is equal to mu naught I over 4 pi my r squared. That's going to be big R squared plus x squared to the half times squared. Yeah. My r, my little r, is big R squared plus big X squared to the half. So that's my r. So that's r. I got to square it. That's what that equation tells me to do, yeah? Well, that's going to all cancel out, isn't it? The half and the square is going to cancel out. So that's that bit done. Better make sure I don't think that's part of my equation. Times 2 pi r. And let's express this cosine theta. If that's theta, cosine theta is adjacent over hypotenuse. So instead of cosine theta, I'm going to say cosine theta is adjacent r over hypotenuse r, which equals r over r squared plus x squared to the half. Yep. So I'm going to write down here cosine theta, and then I'm going to substitute in. So I'm going to get mu naught I over 4 pi. Let's just put this r squared plus x squared. R squared plus x squared. To the half times 2 is to the 1, so just leave it alone. Times 2 pi r, leave that alone, times r over r squared plus x squared to the half. Let's take that, I'm going to simplify it. So that's going to be mu naught I over. Now let's have a look. I can get rid of that pi. That pi goes with that pi, so that goes away. And that 4 cancels, and that 2 cancels with that 4, so that leaves me with a 2, so those 2 are taken care of. And then I've got an r on top and another r on top, so there's my r squared. And then I have, oh yeah, r squared plus x squared to the 3 over 2. Yay! Then you substitute 1%. So why am I showing you that? It's kind of like, it's like traditional physics. And why am I showing you it? Because I want you to be, first of all, realizing that apply the principles and use your math, and you can figure stuff out. Don't be cornered by an equation that looks complicated. It's made of elements that are understandable. And you can, with practice, you can recognize bits like, you know, the r squared plus the x squared to some either a half or 3 over 2. Oh man, that's something to do with Pythagoras. So you can get a hint from that. And also recognize this is one of these things where it's kind of like, again, I used to worry about how did they know not to include little r in the answer? And they know because they know what answer they're working for. You know to get rid of the little r because it's not in the answer, so you just substitute out for it. And I would worry about how would I know to do that, rather than saying, well, it's not in the answer, so I better get rid of it. So be quite pragmatic about it. But don't. If you never look at this, it's going to put you in a corner every time you see it. But if you look at it and play with it, it's going to be, everything gets a bit easier. It's like if you never comb your hair before, your wedding day, then it's going to be really hard on that day. But if you comb your hair every day, then on that day it's going to be fine. It'll just fall into place. So, how am I doing for time? 10 minutes. Okay, magnetic force between two parallel wires. So FB over, I got to apologise for this, just the way the book does it, but FB over, you see, I'm reluctant to use big L because big L is going to mean inductance in a chapter or two. So let's go the other way. Let's do curly L. We'll do curly L. So FB over curly L, the force per unit length between two current carrying wires. Well, logically, it's going to, if I increase the current in one wire, I'm going to get more force. Increase the current in the other wire, I'm going to get more force. And it's going to have something to do with the distance between. So the distance between is A. And you can kind of see from electric field or magnetic field effect, you know, the magnetic field is spreading out over a circle, and the circumference of the circle is 2 pi A. So it's not proof, but it's figuring it out. This is not derived. This is just introduced. At the K, no, this is a curly L. Okay.
Oh, it's 2 pi A.
This is an A down here. That's an A. Okay. So consider two parallel current carrying wires. The force per unit length is given by, so know that equation. When both wires carry a current in the same direction, the force is attractive. How can we show that? Is the current carrying in one direction? Is the current going in the same direction? Let's only think about the right-hand wire. So, corkscrew right-hand rule says my magnetic field is going to go like that. So there's my B. And then use the right-hand rule. This is I cross B. I's coming out. B curls in that direction. B is downwards. That goes round. So here it's going downwards. So I's coming out. B is downwards. I's coming out. B is downwards, and my thumb is down. I is coming out. B is downwards. Got to move my hand, so my force is in that direction. If I reverse it and do the other way around, so now my magnetic field is going to be in that direction. So there's my B coming out. I get an F like that. So either way, when you have current in the same direction, you're going to get attractive force. And if they're in opposite directions, you're going to get repulsive force. That's just the way it's going to be. In fact, this is interesting. The people who do standards and measurements, people at NIST, the people who are responsible in the end for making sure that a second is a second and a Newton is a Newton. And in a trivial way, when you go and buy, 4 ounces of luncheon meat, this 4 ounces of luncheon meat, when you pay for so many kilowatt hours, you're paying for so many kilowatt hours of electricity. When you buy a gallon of gasoline, it really is a gallon of gasoline. We have government agencies to do that, and that's without that, people will be ripped off all over the place, either by accident or on purpose. So we need stuff like that. They not just do the simple stuff like that, they do more complicated stuff, and they try to make measurements more and more kind of way independent. I mean, a kilogram was defined by some French people who got a bunch of iridium together and basically said that's a kilogram, and they put it under a bell jar and pumped the air out to preserve it as long as possible. And a meter was of length of rod, basically. And you had to, when you bought a meter ruler, that factory had to make meter rulers that were scaled to a scale which eventually could trace its provenance back to that meter ruler in France. Hundreds of steps. And that's not trivial, actually. If you think about Lego, I got Legos back in 58. I probably got my first Legos when I was about 4 or 5. 1958 was a long time ago, 60 years ago. And the big ones never changed. The normal size ones, I think of normal size ones, never changed. Maybe 1 centimetre by 1 centimetre. Then they made little ones, now they made big ones. And as far as Lego's concerned, you should be able to take a Lego from any part of the world and put it with another Lego from any part of the world, and it should fit and hold but not be too tight and not fall out. And you should be able to take a Lego that was made 40 years ago and put it with a Lego that's made today and have it fit, not be too tight and not fall out. That's repeatability over a scale which has probably never been done before in humankind. And yet they do it and they maintain it. I'm sure they're not using the same machines they used 50 years ago. And if they did, they would not work because they would get loose and slack and the molds will get bigger and all that. So doing repeatability, doing scales, weights and measures is not trivial stuff. And in Washington, in Gaithersburg, Maryland, we have the National Institute of Science and Technology, some of the really smartest scientists working on this kind of stuff. Not just working on, how long is a meter, but different ways of measuring things. Problem with a meter is, do you have to go to France? France is nice, but do we have to go back there all the time? If we could find a meter defined in some other repeatable way in other labs, it would be really good. And so they use so many wavelengths of light to measure the meter. And then we can all set up a laser and we can all do it. And the same thing goes for this. If you want to measure an amp is a coulomb per second flowing, a coulomb per second. That's a certain number of electrons per second flowing. Man, that's a tough thing to measure. They used to use galvanic cells and, it would be a total pain. Then they realized, we can just use the force between 2 parallel wires. So what they define the amp now as when magnitude of force per unit length between 2 long parallel current wires is 2 times 10 to the minus 7, that should be newtons per meter. Then each wire has an amp flowing through it. So it's a nice little thing. Consider 2 parallel wires. One wire carries a current of 5 amps to the right. The second wire carries a current of 4 amps to the left. The wires are separated by a distance of 2 meters. Are the wires attracted or repelled? If they are, the wires, 2 parallel wires. One wire carries to the right and the other one carries to the left. Opposite directions. I find opposite directions repulsive. When I'm driving down the road and I see the traffic coming opposite me, I go, ugh, repulsive. Or you can basically do it like that, and you say, okay, that's coming into the board, so that means my B is going to be there. I cross B gives me F. So you can figure it out, or you can remember it. I try not to remember, I try to figure things out. So it'll be repulsive. And then what is the magnitude? So what do we say? What is the magnitude of the force per unit length? Can I say that? F over curly L is equal to mu naught I1, I2 over, it's something to do with the circumference of a circle, 2 pi A. Mu naught, it's going to be 5, 4 over 2 pi times, distance between them is 2, which equals 20 mu naught over 4 pi. So, handy dandy calculator, 20 divided by 4, enter, divided by pi, enter. Got a little alarm bell going off in my head, but I'm just going to write this down and then I'm going to think about it. So this would be 1.6 mu naught, and it would be, of course, in newtons per meter. Don't forget units. Now, have I got something going off in my head? Let me just double check this math. That is no, that looks right to me. Okay. Cool. want you to find your pi's. Yes.
How can we use the
Sorry?
hand rule when the current go in different directions?
Well, you pick the magnetic field caused by one current. So I'm using my right hand rule on one of those currents. So the first rule I'm using is my corkscrew rule. And I'm saying that that current is flowing into the board. And so when I do my corkscrew rule, that tells me that my magnetic field is going like that.
So this current is that's going in or going out?
Which one, the left or the right?
The one that you used this one?
This one?
No, the other one.
That one is coming out. We have an arrow. Remember, it's the arrow with the tail feathers. So when you look at the thing coming towards you, you see the tip surrounded by a wire. When you look at the thing coming away from you, you see the X. Yeah. So that's looking from the back. When the thing's coming away from you, arrows go forwards. Yeah. So that means that current's coming out. So we have I cross B and my thumb points away. Yeah. Cool. Cool. I'm going to draw a line there. Let's take a 5-minute break because we're going to come back with Ampere's law. So let's just. I'm going to do 3 minutes.